Hello students, in the last lecture we introduced the basic concepts of probability and random variables. We noted that random variables are functions from the sample space to the set of real numbers. Like other functions, random variables also can be interpreted as members of a vector space, and many results of linear algebra can be extended to random variable theories. Such interpretations are exploited in statistical signal processing. In this lecture, we will introduce the basic concepts of linear algebra and their extension to SSP. We will start with the concept of vectors and scalar. We are familiar with vectors as physical quantities with magnitude and directions, and scalars with magnitudes only. We are familiar with those concepts in physics. Let us recall the notions of vector addition and scalar multiplication. If V and W are vectors and R is a scalar, then vector addition is V plus W and scalar multiplication is RW. Now, in a two-dimensional plane, if we write this is V, this one is W, then V plus W is given by this. This is the vector addition. Similarly, if W is a vector, then we can scale it by a factor R. So, that RW, this is the new vector RW is a scale version of W, and R can be bigger than 1, then this factor will be extended this side. These are the vector addition and scalar multiplications are two basic operations on vectors. The properties of vector addition and scalar multiplications are formalized to define a vector space. So, we will go to vector space now. Vector space, consider the set of real numbers R and a set V. A belonging to R is called a scalar. Any real number we will call it as a scalar. It may be a complex number, but we are considering the scalar of real numbers only. V belonging to V is called a vector. The elements of this space, this set V is called vectors. Suppose two operations called vector addition, that is denoted by plus, and scalar multiplication are defined on V. V is called a vector space if the following properties are satisfied. There are a number of properties. First properties are of vector addition. So, first one is known as the closure property. So, for any vector V W belonging to V, V plus W, vector addition of V and W is also a member of V. So, that way vector addition is closed, or this set of vector is closed under vector addition. Now, vector addition is associative. What does it mean? For any vectors V and W, V, W and Z, V plus sum of W plus Z is equal to sum of V plus W plus Z. So, if we do this sum first and then add to V, it will be same as you first take the sum of V plus W and then add to Z. So, that way this property is known as the associative property of vector addition. Similarly, there is a the vector 0, it is a member of the vector space such that V plus 0 is equal to 0 plus V. V plus 0 is equal to 0 plus V is equal to V. So, that way if we add 0 to the vector, any vector, it will remain the same vector. And V has also an additive inverse. So, for each V belonging to V, there exists a minus V, that is the negative of the vector, such that V plus minus V is equal to 0. And finally, vector addition is commutative. What does it mean? V plus W is equal to W plus V. So, if these properties are satisfied, these 5 properties are satisfied, then V is V plus vector space V and that operation plus are known as a commutative group. These properties are known as the group properties. So, that way vector addition forms a group on the vector space. Okay. So, that way we see that to define vector space we need vector addition, and vector addition satisfy these 5 properties. Similarly, properties of scalar multiplication, we have the following properties. What are those properties? For any Rs belonging to R, R and S are scalars, and Vw belonging to V, V and W are vectors. Suppose closure property, that is scalar multiplication of V with R, Rv belongs to V. If we multiply a vector by a scalar, we will get another vector. Associativity, so R into SV is equal to Rs into V. So, that way first we can scale V, then we can scale SV. This is same as scaling V by factor Rs. Distributivity with respect to vector addition. So, here 2 operations are there, vector addition and scalar multiplication. So, we have to consider distributivity with respect to vector addition, that is R of V plus W is equal to Rv plus Rw. Similarly, with respect to scalar addition also, scalar multiplication is distributive. So, that we can write as R plus S into V, that is same as Rv plus Sv. So, distributivity with respect to scalar addition. So, if we add 2 scalar R plus S into V, that will be same as Rv plus Sv. So, this is the distribution with respect to scalar addition. And also we have the unity scalar, 1 into V is equal to V. So, therefore, in a vector space 2 operations are there, one is scalar multiplication, one is vector addition, and vector addition satisfy 5 properties, scalar multiplication also satisfies these 5 properties. So, we have defined a vector space. Now, we can give some example, simple examples are there. For example, if we consider suppose normal vectors in a 3-dimensional space, and then the collection of those vectors will form a vector space with respect to vector addition and scalar multiplication. We will give another example. Suppose let S be an, this example is important for us. Let S be an arbitrary set and V be the set of functions from S to R. Suppose f from S to R and g from S to R are 2 functions, and S and R are 2 elements of S. Then by definition f plus g s at point S, f plus g at the point S is equal to f s plus g s, and also a f of S, a f at point S is equal to a times f of S. So, that way since we are considering all function, this is also a function, this is also a function, thus V is closed under addition of functions and multiplication of function by a scalar. You are multiplying a function by a scalar, you are getting another function, and similarly you are adding 2 functions, you are getting another function. That way the space of all functions are closed under addition of function and scalar multiplication of a function with any scalar. Thus, V is closed under addition of functions and multiplication of a function by a scalar. It is easy to verify that these operations satisfy the properties of the vector space. So, that addition of function is associative. Similarly, we can define a 0 function, and other properties of scalar multiplication also we can establish. So, therefore, what we say that the set of all functions from any set S to R is a vector space with respect to addition of function and scalar multiplication of function. Now, random variables are functions on the sample space S. Therefore, the set of all random variables form a vector space with respect to addition of random variables and scalar multiplication of a random variable by a real number. So, that way this is one important result. What we say that random variables form a vector space with respect to the addition of random variables and scalar multiplication of a random variable by a real number. The set of random vectors also form a vector space where the operations of addition and scalar multiplications are defined as the corresponding operations on the component random variables. So, that way we can define a vector space of random vectors also. Let us define a subspace. Suppose W is a non-empty subset of V. W is called a subspace of V if W is a vector space. It itself is a vector space with respect to the same operations of vector addition and scalar multiplication defined on V. So, W is a subset and it itself is a vector space with respect to the operations of the original vector space. For a non-empty subset W to be a subspace of V, it is sufficient that W is closed under vector addition and scalar multiplication of V. Thus, the sufficient conditions are for all VW belonging to V, V plus W should also belong to W. For all V belong to W and R belonging to R, RV also belong to W. So, these are the properties needed for a subset W to be a subspace. We can show that 0 is an element of this subspace and other properties of vector space are satisfied by subspace also. Example, we will consider one example. Suppose V is the vector space of all random variables and W is the set of all zero mean random variables. Now, if we add two zero mean random variable, you will get a zero mean random variable. If we multiply a zero mean random variable by a scalar, you will get a zero mean random variable. Therefore, W is a subspace of V. So, in the case of the vector space of random variables, we can define another subspace, that is this subspace of the zero mean random variables. Now, for the vector space, linear independence and basis are two important concepts. Consider a subset of n vectors, that is B is equal to B1, B2 up to Bn, and n scalars C1, C2 up to Cn. Now, if C1 B1 plus C2 B2 plus up to Cn Bn is equal to 0 vector, implies that C1 equal to 0. If this is equal to 0, then C1 must be equal to 0, C2 must be equal to 0 and so on. Then B1, B2, Bn are called linearly independent. This we abbreviate as Li. So, if this left hand side is equal to 0, then all the coefficients must be identically 0. Then we will say that these vectors are B1, B2, Bn are linearly independent. Linear independence says that suppose any vector, if we consider in this set B1, B2 up to Bn, you cannot represent one vector in terms of the rest, one vector as a linear combination of the rest. For example, let us consider this two dimensional vector. Suppose this is my B1 and this is my B2. Normally, when we write by hand, we give a bar to denote a vector. Now, this B1 cannot be written in terms of B2, or we cannot write B1 as a scale version of B2. Therefore, B1 and B2 are independent. However, if we have another vector, suppose B3. Now, this B3 can be represented in terms of as a linear combination of B1 and B2. Therefore, B1, B2 and B3 in this case will not be linear independent. So, we introduce the concept of linear independence. Linear independence basically means that in those collection of vectors, one vector cannot be expressed as a linear combination of the rest. Now, we will tell what is a basis. The subset B is equal to B1, B2 up to Bn of n Li vectors is called a basis if V belonging to V can be expressed as a linear combination of elements of V. So, there are n elements and we can express any vector in V as a linear combination of these n vectors, and in that case n is called the dimension of V. Therefore, what is a basis then? Basis are those vectors which are linearly independent and their linear combination can generate any vector V belonging to the vector space. Now, we told that random variables also form a vector space, but unfortunately the dimension of this vector space is infinite and finding a basis for this vector space is a complicated task. Norm of a vector. We know that suppose in a two-dimensional vector I have the length of the vector, and the concept of length can be generalized for a vector space. Suppose V is a vector in a vector space V defined over R. The norm denoted by this notation. So, norm of V is a scalar such that for all V W belonging to V and R belonging to R, these four properties are satisfied. So, number one is norm is non-negative. So, norm of V is always greater than equal to 0. Then when norm will be equal to 0? Norm will be equal to 0 only when V is equal to 0, that vector itself is 0 vector. Then norm of a scalar multiplication of a vector is equal to norm of the scalar, that is magnitude of the scalar, because scalar is a real number. So, it is a magnitude of the scalar multiplied by the norm of the vector. Now, fourth property is important, that is we know this is the triangular inequality. Suppose in the case of length, we know that suppose if we in any triangle, if we consider this third side will be less than equal to sum of these two sides. So, this result is, that is norm of V plus W is less than equal to norm of V plus norm of W. This is the triangular inequality. So, any measure that satisfies these four properties qualifies to be a norm. For example, in the case of vector space of random variables, root over E of x square is a norm. Similarly, we can have suppose E of mod of x, that is also a norm. So, here we see that since it is a random variable, that to define norm we are taking the help of expectation operation, because this expectation operation will convert it into a scalar. So, we have defined norm. Now, we will define what is an inner product between two vectors. The inner product is the generalization of the dot product between two vectors. Suppose I know that if A is a vector, suppose B is a vector, A dot B is equal to magnitude of A into magnitude of B into cos of angle between them, cos of theta. So, now this dot product, vector dot product satisfies certain properties, and these properties are generalized to define the inner product of two vectors. If V W belong to capital V, the inner product, this is denoted by, that is angular bracket V W, is a scalar. So, inner product is a scalar such that for all V W Z belong to V. So, any three members of V and R belonging to R, what will happen, that inner product of V W is equal to inner product of W V. So, inner product is commutative. This property is known as symmetry property. Inner product of V W is equal to inner product of W V. Now, what happens if we take the inner product with itself? So, inner product of V V is equal to norm of V square, which is greater than equal to 0. Now, where Now, this norm of V is a norm induced by the inner product. From inner product itself, we can induce a norm. What is that norm? That is the inner product of V with itself. So, that way inner product will define a norm. Third property is inner product of V plus W Z is equal to inner product of V Z plus inner product of W Z. This is the third property. And fourth property is, if we scale one vector, suppose R, inner product of R V W is same as R times inner product of V W. So, these are the properties also satisfied by dot products. It is very easy to verify, and here we will be using these properties as the definition of inner product. A vector space V where an inner product is defined is called an inner product space. Now, from vector space we have come to inner product space. In fact, when norm is defined, that vector space is known as the normed linear space or normed vector space. Now, we have defined normed inner product space. Joint expectation as an inner product operation. Considering random variables x and y as vectors, it is easy to verify that E of x y, because we know that E of x y is a real number, it is a scalar, defines an inner product of x and y. For example, E of x y is equal to E of y x. Now, E of x square will be always greater than equal to 0. Like that, all other properties we can show to be satisfied. Therefore, this joint expectation of x y is an inner product operation. So, that is a very important conclusion now. E of x y defines an inner product of random variable x and y when they are represented as vectors. And this inner product induces a norm. What is that norm? Norm of x square, that is equal to E of x square. So, we can define inner product of two random variables. Similarly, for two random vectors also, random vectors x is equal to suppose this and y is equal to this, then inner product we can define as E of x transpose y. X transpose y will convert these two vectors into scalar, and then this scalar, when we take the expectation, we get the inner product. Okay. So, x transpose y, that is a scalar, and when we take the expectation, we get the inner product. So, we have defined inner product. In the case of inner product, there is a very important inequality, what is known as Cauchy-Schwarz inequality. Recall that in the case of dot product of two vectors, that is magnitude of A dot B is less than equal to magnitude of A into magnitude of B. This is because cos theta is, magnitude of cos theta is less than equal to 1. So, from the definition of dot product, this result follows. CS inequality, Cauchy-Schwarz inequality generalizes this inequality into the following inequality. How it is generalized? If V is an inner product space, vector V, this V is a inner product space, and small v w belong to V. If V is an inner product space and small v w are members of V, then magnitude of the inner product of V and W is less than equal to norm of W into norm of V. So, this is a very important result. Cauchy-Schwarz inequality. We will not prove this, but we will assume that it is satisfied. This CS inequality will be used to derive an important result of joint random variables. So, we can interpret covariance of x y. Suppose covariance of x y is equal to, by definition, E of x minus mu x into y minus mu y. So, this is an inner product on these two random variables x minus mu x into y minus mu y. Now, since it is an inner product operation, we can apply Cauchy-Schwarz inequality. What we will get? That is, if we take the magnitude of this, that is same as magnitude of this quantity, and that must be less than equal to, now inner product is less than equal to norm. Here what is the norm? Norm is x minus mu x, expectation of x minus mu x whole square, square root of that. Similarly, norm of this quantity is expectation of y minus mu y whole square and square root of that. So, what we get therefore, applying the Cauchy-Schwarz inequality, covariance of x y is less than equal to square root of e of x minus mu x whole square into square root of e of y minus mu y whole square, and these quantities are nothing but variance. So, and if we take the square root, then we will get sigma x. If we take the square root of this, we will get sigma y. So, therefore, covariance of x y divided by sigma x into sigma y, its magnitude, because I am taking to the denominator of this must be less than equal to 1, and this quantity is the correlation factor. So, covariance of x y divided by sigma x into sigma y, it is known as the correlation coefficient, and we see that magnitude of rho is always less than equal to 1. So, this is one important result. Now, let us see relation between uncorrelated and independent random variables. Note that covariance of x y equal to 0 implies that rho is equal to 0. Therefore, x and y are uncorrelated if rho is equal to 0. This can be taken as a definition. Now, suppose x and y are independent, then by definition joint density is product of the marginal density for all x y. Now, you multiply both sides by x y and take the double integral with respect to dy dx, and now using the separability we get that this is equal to integration of x fx of x dx into integration of y fyy dy. So, and this is e of x and this is e of y. So, e of x y is equal to e x into e y. That is, if x and y are independent, then they are uncorrelated. Independence implies uncorrelatedness. The converse is not generally true. So, uncorrelatedness does not imply independence in general. However, if x and y are jointly Gaussian and uncorrelated, then x and y are independent. We can see this. If x and y are jointly Gaussian and uncorrelated, then x and y are independent. To prove this result, consider a jointly Gaussian PDF with rho is equal to 0. We know what is the jointly Gaussian. This density function is given by 1 by 2 pi sigma 1 sigma 2 into root over 1 minus rho square into e to the power minus half of these quantities. Okay. Now, uncorrelated x and y are uncorrelated Gaussian, therefore, rho is equal to 0. If I put rho is equal to 0 here, I will get this expression, and this rho will be equal to 0, therefore, this will be 1 only. So, I will get this expression. Now, I can separate out these two factors, so that I will get this one PDF here and this is another PDF. This is the PDF of x and this is the PDF of y. So, in this case joint PDF is equal to the product of the marginal PDF. We should also recall that if x and y are jointly Gaussian, then they are individually also Gaussian. Therefore, this is the PDF of x and this is the PDF of y, and joint density is product of marginal densities, therefore, x and y are independent. So, the concept of inner product can be used to define orthogonal vectors. Two vectors v and w belonging to an inner product space V are called orthogonal if the inner product of v and w is equal to 0. Just like in the case of three-dimensional space, suppose when the vectors are perpendicular, then inner dot product is 0. The same concept is used here. Two vectors will be orthogonal when their inner product is equal to 0. Now, consider 3D vector space of position vector R3, that we generally denote by R3. Then the vectors I, j, k. This is the, suppose, I vector, this is the j vector, and this is the k vector, suppose, and they are orthogonal. So, these vectors are orthogonal. So, the vectors I, j, k are orthogonal, because here inner product is the dot product between I and k will be equal to 0, dot product between I and j will be equal to 0, like that. Now, orthogonal vectors are independent. That is one important result, that orthogonal vectors are independent, and I, j, k are orthogonal. Therefore, I, j, k also will be independent, and therefore, now we know that these n independent orthogonal vectors, because they are independent, they will form a basis of the n dimensional vector space. So, that way, if we have orthogonal vectors, n orthogonal vectors, then those n orthogonal vectors are basis of n dimensional vector space, and therefore, this I, j, k is a basis for R3, because I, j, k are independent and this is 3 dimensional space. Therefore, this is a basis. So, now this concept of orthogonal vectors can be generalized to orthogonal random variables. Now, orthogonality of vectors can be extended to random variables. Two random variables x and y are called orthogonal if inner product of x y, that is equal to E of x y, equal to 0. If E of x y is equal to 0, then x and y are called orthogonal. Example, suppose x and y are random variables with same mean and same variance. So, both mean and variance of x and y are equal. So, in that case, x plus y and x minus y are orthogonal. How? Suppose x plus y E of into x minus y, that is equal to E of x square minus y square, that is equal to E of x square minus E of y square. Now, since both are of the same mean and variance, therefore, E of x square and E of y square are equal, that will be equal to 0. We will see that orthogonality of random variables plays an important role in estimation theory. Particularly, we will see that for optimal estimation, error is orthogonal to data. This result we will be using. So, we have defined orthogonal random variables and uncorrelated random variables, but how they are related? Two random variables x and y are uncorrelated if E of x y is equal to E x into E y. That is covariance of x y is equal to 0. From that we get that E of x y is equal to E x into E y. Now, if either E x is equal to 0 or E y is equal to 0, then E of x y is equal to, now since one of E x or E y is 0, therefore, this product E x into E y will be equal to 0. So, therefore, 0 mean uncorrelated random variables are orthogonal. Such random variables play important role in modeling of random signals. For modeling random signals, we need a sequence of 0 mean uncorrelated random variables. In fact, they are orthogonal. Let us summarize the lecture today. A vector space V is defined with respect to two operations, vector addition and multiplication of a vector by a scalar, and those properties of vector addition and scalar multiplications must be satisfied. The set of all random variables forms a vector space with respect to the addition of random variables and scalar multiplication of a random variable by a real number. The norm V of a vector V is a non-negative scalar. So, we define norm is a non-negative scalar satisfying 4 properties, and square root of E x square is a norm of the random variable x. The inner product V w of two vectors V and w is generalization of the vector dot product. Inner product is a generalization of vector dot product and is a scalar. Inner product is a scalar satisfying 4 properties, those properties we stated. Then we introduce the Cauchy-Schwarz inequality is given by magnitude of inner product of VW is less than equal to norm of W into norm of V, and we define the ratio rho is equal to covariance of xy divided by sigma x into sigma y. This is called the correlation coefficient. The Cauchy-Schwarz inequality was used to prove that magnitude of rho is less than equal to 1. We used Cauchy-Schwarz inequality to show that the magnitude of the correlation ratio is less than equal to 1. For uncorrelated random variables x and y, rho is equal to 0. So, since they are uncorrelated, rho is equal to 0. If x and y are uncorrelated Gaussian, then they are independent also. Using the joint PDF of the Gaussian random variables, we showed that if rho is equal to 0, then x and y are independent also. Generally, independent random variables are uncorrelated, but uncorrelated does not imply independence. Only in the case of Gaussian, if they are uncorrelated, then they are independent also. Two random variables x and y are called orthogonal if inner product of xy, that is equal to E of xy, equal to 0. 0 means uncorrelated random variables are orthogonal and they play important role in the modeling of random signals, that we will be using in a future lecture. Statistical signal processing also uses matrix theory extensively. We will not cover matrix theory in this lecture, but we will be introducing it whenever application comes. In the next lecture, we will give the foundation of random process. Thank you.